The tallest building in Southeast Asia climbed floor by floor in months, not years. 14-ton walls assembled flat on the ground, then lifted vertical in one pick. Every skyscraper on the skyline hides a system almost nobody ever sees. Stick around to the closing stretch to watch the same machine build an entirely different tower in Paris. Look up at any skyline mid-construction and the buildings are almost secondary. The real show is the cranes. A downtown high-rise site is a forest of steel arms swinging above traffic, and every one of them had to be raised from a pile of parts before the tower could think about going anywhere. Each tower crane rolls in on trucks as a stack of mast sections, a jib, a cabin, and a slewing platform. Ground crews bolt the base into a reinforced concrete pad, then a mobile crane stacks the mast segments upward, one at a time. The angled jib, often 30 to 70 meters long, goes up last. Workers walk out along it a few hundred feet above the street to connect the cables. The safety brief for that morning is not a short read. Once assembled, the crane can hoist several tons at a time. That capacity quietly sets the ceiling on how fast the entire tower is allowed to grow. Now watch what those cranes are lifting toward. A time-lapse compresses years into a minute. A 492-meter tower climbs floor by floor into the tallest building in Southeast Asia. Steel, concrete, and glass appear to sprout out of the ground. But something that heavy does not stay upright by accident, and the reason lives where no cameraman bothers to point. Before anyone pours a drop of concrete, somebody has to know what is actually under the site, and the surface is a terrible witness. A parking lot may look solid, but 10 meters down could be soft clay, an unmapped groundwater layer, or a rock shelf tilted at exactly the wrong angle. To find out, a small drilling rig punches a narrow borehole straight into the ground. Workers connect drill pipes one at a time, feeding the rod deeper as the rig grinds through each layer. Every so often, drilling pauses for the standard penetration test. A heavy hammer drops onto the rod from a fixed height, and the number of blows needed to drive the sampler a set distance tells engineers how dense the soil really is. When the drill hits rock, the routine shifts to coring. A hollow diamond bit cuts a clean cylinder of stone, which comes up in a wooden sample box labeled by depth. That box of little tubes is basically the building's medical history before it exists. Pile depth, wall thickness, foundation type. Every future decision is written in there, but knowing what is down there is the easy half. Putting steel and concrete deep enough to catch it is where the trouble starts. This is where the ground stops being a mystery and starts becoming structure. A large rig with a continuous flight auger, basically a giant corkscrew, drills straight down while lifting soil to the surface. The clever move happens on the way back up. As the auger retracts, high-pressure concrete pumps through the hollow center, filling the shaft from the bottom before the walls have a chance to collapse inward. Only after the shaft is full does a crane lower a long rebar cage into the wet concrete. One rig, one shaft, no dramatic pauses to see whether the sides feel like holding today. Take that same idea and push it down where most buildings never have to go. On the Vienna U2-U5 metro expansion, crews installed the deepest bored piles ever built in the city. Reaching 61 meters, shaft diameters of 1,180 millimeters. Below 30 meters, the shaft is held open by bentonite slurry that pushes back against the surrounding soil. A dedicated mixmaster on-site checks salt content and viscosity all shift, because if the slurry weakens, the whole hole can pinch shut before the concrete truck arrives. 61 meters! You're basically drilling 20 stories of building underground before a single floor exists above. Concrete on its own will crack under a skyscraper. It needs a skeleton first. Workers cut long rebar rods to length, bend hoops on a table jig, then tie the vertical bars and spiral hoops together into a cylindrical cage, sometimes 20 meters long. Every intersection is wire-tied by hand. The cage looks flimsy right up until you remember it is signing a 100-year contract with the tower above. Not every foundation problem calls for a drilled hole. Sometimes crews need a temporary retaining line along the edge of a site, and for that they press interlocking sheet piles directly into the ground. A tracked rig with a sheet pile press can push 4 panels at once, up to 800 millimeters wide, without hammering or vibration. A worker stands off to the side, running everything on a remote, and the mast even rotates to press corners inside tight pits, which becomes very important when the neighboring building starts 1 meter away and belongs to someone with a lawyer. Try digging a 5-story hole in downtown Perth without the streets around it sliding in. That is the puzzle a diaphragm wall solves. And it does it before the excavator has scooped a single load. A crawler crane fitted with a hydraulic grab. Basically a giant clamshell bucket. Choose a rectangular trench straight down, 1 panel at a time. The moment the grab lifts material out, bentonite slurry pours in to keep the trench walls from folding inward under earth pressure. Each panel on this Perth site runs 15 to 20 meters deep at 600 millimeters thick, and 55 of them ring the future basement. Once a panel reaches design depth, a prefabricated rebar cage is lowered in through the slurry. Then a tremie pipe drops to the bottom, and concrete is pumped upward, displacing the slurry from below. The slurry rises out the top and gets recycled for the next panel. The result? A continuous underground wall installed before 1 truckload of soil leaves the site. With that ring in place, the neighbor's foundations stop being an active concern. But holding the sides is only step 1. The middle still has to come out, and gravity has no interest in cooperating. When a project sits shoulder to shoulder with older buildings, hammered piles are usually off the table. The vibration alone can crack neighboring facades and hand the developer a very expensive Tuesday. That is why crews on tight urban sites often lean on board piles instead. A surveyor first locks each pile position with a theodolite. An auger rig drills a primary hole 20 to 30 meters down. A steel casing is lowered by a vibrating hammer and checked for vertical accuracy with a plumb, because a pile leaning even a couple of degrees at the top can end up badly out of place at the bottom. Then a drilling bucket cuts to the final depth while polymeric slurry is pumped in to keep the shaft open. Chosen over bentonite here because the site is cramped and polymer is easier to dispose of. A 12-meter rebar cage is lowered and welded to the casing. A tremie tube feeds concrete from the bottom up, forcing the used slurry out the top for reuse. The casing gets pulled once concrete is placed, and the shaft cures. Freshly poured piles always finish with an ugly problem at the top. The upper meter of concrete mixes with slurry and comes out weak, so it has to go, without damaging the rebar underneath. A hydraulic pile cropper clamps around the shaft and snaps off the bad concrete in 1 clean pass, leaving clean rebar sticking up to bond with the pile cap. Vienna's foundation crews built 1 skyline. Anyone here want to weigh in on how the pile depth problem gets solved on your bedrock versus theirs? Hundreds of these piles ring and stud the site, and now something enormous has to land on top of them all at once. Everything below now has to transfer its purpose into 1 enormous slab. For a 600-foot commercial tower in Bellevue, that meant a mat foundation pour of roughly 10,000 cubic yards, planned for years. Because the street outside had buses, pedestrians, and no room for pump outriggers. The fix? Fly the pump trucks into the pit with a crane. 6 pumps below, 12 mixers on the street, 700 cubic yards per hour. A pour this size is a logistics test dressed up as a construction task. For the Salt Lake City Airport tunnel slab, crews placed 1,700 cubic yards of concrete in a 4-foot thick mat during a continuous 8-hour pour, and every truck arriving late risked breaking the whole chain. 2 boom pumps stood over a dense rebar grid while workers on the surface guided the discharge hoses into the correct grid squares. A cold joint, where fresh concrete meets concrete that has already begun to harden, would create a weak plane through the structural mat and force expensive remediation, so the trucks do not stop. Behind the pumps, A rotating queue of mixers waited on the access road, each timed so the pump hopper stays full without overflowing. On the slab, workers used vibrators to consolidate the mix around every rebar intersection, chasing air pockets out. Screed teams followed, dragging boards across the surface to level it. A mixer breaks down 90 minutes in, and the queue slips 15 minutes. Do you throttle the pumps, redirect trucks from a sister job, or eat the risk and keep going? Drop your call below. Once the mat is solid, the next challenge is carrying that load upward through steel. With the foundation done, the load path now has to march upward, floor by floor, through vertical steel bars buried inside every column. The catch is that rebar comes in lengths measured in single-digit meters, and a high-rise column can climb hundreds of them. A mechanical coupler solves this by joining two bar ends inside a steel sleeve. No welding, no lapped bars crowding the concrete cover. In a trial simulating a 1,000 by 1,500 millimeter column, crews erected 2036 millimeter monkey bars as freestanding vertical elements, each locked in place by a retaining sleeve sliding over the joint. A prefabricated tie cage was lowered by crane over the tops, aligned onto protective caps, and the whole column stood in under 7 minutes. Crane time is billed by the hour, and it is not cheap. Every minute the hook is idle costs more than most people make in a day. With the foundation done, the load path now has to march upward, floor by floor, through vertical steel bars buried inside every column. The catch is that rebar comes in lengths measured in single-digit meters, and a high-rise column can climb hundreds of them. A mechanical coupler solves this by joining two bar ends inside a steel sleeve. No welding, no lapped bars crowding the concrete cover. In a trial simulating a 1,000 by 1,500 millimeter column, crews erected 2036 millimeter monkey bars as freestanding vertical elements, each locked in place by a retaining sleeve sliding over the joint. A prefabricated tie cage was lowered by crane over the tops, aligned onto protective caps, and the whole column stood in under 7 minutes. Crane time is billed by the hour, and it is not cheap. Every minute the hook is idle costs more than most people make in a day. This is what that crimp looks like at working scale. Two workers feed rebar ends into a splicing sleeve, then a hydraulic ram compresses the whole assembly in seconds. The joint matches the strength of solid rebar, which becomes very important in earthquake country, where every splice will eventually get audited by nature. When couplers are used at scale, entire walls can be assembled flat on the ground and lifted into place as one piece. On the Back River project in Baltimore, crews built a 14-ton pre-tied wall on the deck, with number 14 vertical bars already fitted with threaded couplers at every splice point. A crane lifted the whole cage vertical in a single pick. Workers on the ground guided it onto the matching bars protruding from the pour below. Then teams with torque wrenches threaded each coupler onto its partner bar, one after another, moving methodically along the wall face. Splicing this way turns a slow tying operation into a controlled assembly. The couplers develop 175% of the bar's yield strength, meaning the rebar itself fails before the joint gives, which is the correct answer for seismic zones. A perfect wall with one bad splice still fails at the bad splice. That is the whole reason this stuff gets torque checked. Real construction rarely lines up as neatly as a shop drawing suggests. Bars come out of the pour slightly off. Cages arrive with tolerant stack-up. The two ends that were supposed to meet perfectly end up a few millimeters apart. A position coupler solves that. It has a threaded body that spins up or down the bar to bridge small alignment gaps, then locks in place, often just hand-tight to start. That is what saves entire days on pre-tied cages and wall installations, where a couple of stubborn bars can otherwise stop an entire deck from moving. Tying rebar by hand, bar by bar, is the slowest part of most concrete decks, and everyone above is waiting on it. Prefabricated rebar carpets change the math. Bars are wired together in a factory into a huge rolled mat with exact spacing built in. On site, a crane lifts the roll into position, workers cut the securing tags, and the whole mat unrolls across the deck. On the Oriole project in London, 4 layers went down as carpets. Then column splice bars were screwed on with couplers. Deck to pour cycle, about 2.5 days. Every floor above waits on the floor below. Save hours, save weeks. Save weeks, keep the job on budget. Fast rebar buys nothing if the formwork above it cannot keep pace. This is the trick that lets a tower keep rising without dismantling formwork every level. At the 4 Frankfurt project, a rail climbing system stayed attached to the concrete core and hoisted itself upward as each pour set. Digital tablet control, 1 trailing platform, tight space capability. Oh, the forms climb with the building. And that is when you realize the whole job is really a factory that moves. Same problem, bigger machine. Luffing jib tower cranes at 4 Frankfurt climbed inside the core itself, jacking themselves higher as the tower rose. Honestly, an internal climbing crane is the wildest engineering move on any high-rise site, and nobody outside the industry ever hears about it. Tell me what you think. Getting concrete to the pit is one problem. Getting it 1,000 feet in the air is a completely different one. The higher a tower climbs, the more a pump truck stops being a truck and starts being an aerial delivery system. Modern truck-mounted booms fold and unfold through several jointed sections, reaching over parked cars, existing walls, and even discharging over the top of the driver's cab in tight setups. Pivoting outrigger legs let the operator plant supports around obstacles, expanding the working area by up to 70%. Hydraulic pressures push up to 320 bars to keep concrete moving smoothly, which is what stops the end hose from snapping around and painting everyone downstream in wet mix. Reach is only useful if the operator knows exactly how far is safe. Modern control systems calculate the working envelope live on a tablet, based on where the outriggers were actually planted on that specific site. A radio remote lets one worker walk the pour and steer the boom directly. Bigger pours, tighter sites, no explanation phone calls to the insurance office at 5 p.m. Past a certain height, the pump truck on the street stops being part of the plan. A placing boom rides directly on the building's jump form system, high above the city. Concrete travels up through pipes and gets placed exactly where the deck crew needs it. The pump climbs with the tower. At some point, doing everything on site simply stops making sense. Precast concrete columns start life in a controlled yard. Engineers finalize the structural drawings. Workers tie the rebar cage. Molds get filled with concrete and vibrated tight, then cured under protective covers. Every finished column gets a scannable label tracking its exact production batch. Trucks deliver them to the tower in the correct install order, where a crane lifts each one straight into position and workers grout the base. Factory concrete showing up right when the crane is ready to swing. That is the whole payoff. Precast solves the fabrication half. It does nothing about vertical logistics. On the Canary Wharf South Quay Plaza project, crews used a suspended formwork hoist rated at 2,500 kilograms to shuttle materials between floors. No tower crane needed, 1 operator, 18 meters per minute. Tower cranes are too expensive to spend the day moving stacks of plywood. A skyscraper under construction has a problem no finished building has: no working elevators. Until permanent lifts are installed and certified, thousands of workers, tools, and material bundles have to reach the upper floors somehow. And stairs stop being a serious answer around floor 10. Rack and pinion construction hoists solve this. A toothed rack runs the full height of a mast bolted to the outside of the building, and the hoist cabin drives itself up and down using powered gears. Meets ANSI A10.4 safety code. Handles personnel and material. Ever tried carrying a 60-kilogram wall panel up 45 flights? Someone actually did, before this thing was invented. On a real high-rise site, 2 or 3 of these hoists run at once on different faces of the tower, cycling all day. They are the temporary bloodstream, until the permanent elevators go live and the hoists come off. The moment a construction site starts to look like a building is when the facade shows up. Full glass modules, some pushing 3.5 tons, get lifted by a manual or electric monorail rig sitting on the slab edge. The tower crane never has to touch them. Every one of those modules started life in a factory hundreds of miles away. In a controlled plant, aluminum profiles run through CNC machines that cut and mill them to precise dimensions. Workers apply certified structural sealant along every glass, edge, and vacuum lifters, which grip glass by suction pads without touching the visible face. Position each pane into its aluminum frame. Quality control is finished before anything ships, because a defective unit found at 30 floors up costs several times what it would have cost to reject in the factory. The finished units are packed in stillages of 4 and loaded onto trucks in the exact order they will be installed. A telehandler unloads them on site. Sealant cures indoors, under a roof, with a QC inspector watching, which is why factory facades outlast anything glazed up on the deck by decades. But arrival is one thing. Getting a 3.5-ton glass box into its final slot without breaking it is another problem entirely. Facade installation is where a strict process protects both the workers and the building. Before anyone touches a panel, method statements and permits are signed, PPE is checked, and exclusion zones go up around every work area, one on the install floor, one at ground level in case anything drops. Panels are unloaded from delivery stillages with a pick-and-carry crane, rotated 90 degrees, and set on rolling platforms with locking wheels. When installation starts, only harnessed operators enter the zone. Handrails at the slab edge come off just long enough to swing the panel outward and lock it to the anchors below. The install crew for a modern curtain wall system is a lot smaller than most people expect. 6 people can handle a floor. That is because the units arrive pre-glazed and pre-sealed. The field crew is mostly placing, adjusting, and locking. First, anchors are surveyed into position using total station equipment. A millimeter off at floor 40 shows up as a visible offset from the street, and pedestrians notice. Anchors are marked in blue once inspected. Then units get lifted by crane in the delivery sequence, usually 4 to a bunk, either from the ground or from inside the building. Each unit locks into its anchors, gets fine adjusted with a rotating laser, then sealed at the seams. Fire foam is cut in between the slab edge and the facade to keep flames from jumping floors. Then smoke seal covers any small gaps. Stool trim finishes the interior. With the outside sealed, the interior finally starts turning into rooms. Drywall crews plan panel layout to minimize joints, usually installing horizontally because fewer seams mean less taping later. Ceilings go up first, secured with screws every 12 inches into the joists. Wall panels follow, with screws every 16 inches into the studs. Joints are staggered away from window and door corners, because that is where cracks start when the building moves. Cutouts for electrical boxes are measured, traced, and cut with a keyhole saw. Bottom panels leave a half-inch gap from the floor for movement. Zoom out from any one process and a real project runs several at once on different cores. RC frame, jump form cores, unipanel walls, precast columns, precast stairs. All sequenced through just-in-time deliveries because ground floor storage is too tight to hold anything. One delivery slot goes wrong and the whole floor stalls. Now, every process shown so far reassembles itself into one image. The Exchange 106 in Kuala Lumpur, 492 meters, top 15 in the world. What started at less than 1 floor per week ramped up to a floor every 2 days once the system's locked in. Watch it happen from the outside. Over 13 months, foundation becomes core, core becomes structure, structure becomes envelope. Blue glass chases the concrete upward. Cranes climb along. The tower stops being a construction site and starts being part of the skyline. Same logic, completely different building. The Tribunal de Paris rose across 4 years using the identical playbook. Deep foundation, structural core, floor-by-floor superstructure, unitized facade. Different architecture, different geometry, different city, same underlying machine. Once you know how these towers actually get built, no skyline ever looks quite the same again. Every tall building on any skyline is really thousands of small cycles stacked on top of each other. Rebar, formwork, concrete, curing, climbing, repeat. Held together by a supply chain that never gets to breathe. The current argument inside the industry is speed versus longevity. Faster cycles, more prefabrication, tighter tolerances. Great for delivery dates and developer margins. But modern buildings are often designed around a defined working life of roughly 50 years, while some major civil structures are designed for 100 years or more. That doesn't mean a tower expires at 50. With inspection, maintenance, and repair, its actual service life can extend far beyond the design period. Where do you stand? Is a 50-year design life simply realistic engineering, or should major towers be designed to last much longer? Drop your take below. Thanks for staying to the end. If watching how these towers actually go together made the skyline look different, tap subscribe. The next video digs into another world most people never get to see.